Good afternoon to everyone and thank you for joining. On behalf of Prime Minister's Museum and Library and Nehru Planetarium, New Delhi, I extend a very warm welcome to all of you to attend this online webinar, Know Your Star, the Sun. It's our complete honor to introduce our distinguished speaker for today, Dr. Rukmini Jagirdar. Dr. Rukmini is an accomplished astronomer and a dedicated educator, currently serving as associate professor in Department of Astronomy at Osmania University, Hyderabad. She holds a PhD in astronomy and has a several years of experience in teaching, research, and science outreach. Her research interest includes stellar structure and evolution, binary stars, variable stars, and observational astronomy. And she has contributed significantly to the field through numerous research publications in reputed international journals. Beyond her research, Dr. Rukmini is deeply passionate about popularizing astronomy among students and general public and has been actively involved in workshops, public lectures, and outreach programs. Today, she will guide us through an engaging exploration of our nearest star, the Sun, helping us understand the nature, behavior, and importance of life on Earth and the fascinating science behind it. We are sure this session will enrich our understanding and ignite our curiosity about the star that makes life possible on our planet. We are truly delighted to have you with us, Dr. Rukmani, and thank you for joining us, for sharing your knowledge with us on our platform. Before we begin,
Thank you very much.
thank you, ma'am. Today we begin the webinar. It's a privilege to invite Dr. Y. Ravi Kiran, Director, Nehru Planetarium, New Delhi, to begin with, to share some few words so that we can start today's session.
Yeah, thank you, Prerna. Welcome, Dr. Rukmini, for this session. I hope you will enlighten us about the star that is Sun and all others. In fact, Sun is the nearest star, and all the stars that we see in the sky are just like Sun. And Sun is also a very natural laboratory that we have. So Dr. Rukmini is who is also from Osmania University. In fact, I am also from Osmania University. So she will enlighten us about this sun. And more than that, I want to talk about little about Nehru Planetarium. Nehru Planetarium was opened in 1984. It is one of the oldest planetariums in India. Now this is part of Pradhan Mantri Sangralay Museum and Library. That is, we conduct many activities apart from shows, planetarium shows. We have 2D and 3D shows, and apart from planetarium shows, we have workshops, then conducting lectures, and many workshops. Then even this lectures every month we have popular lectures from.
I think we're having some little lag in Sir's video.
Yeah.
So let me continue what Sir was telling us, that we do in the planetarium is doing a lot of work in science popularization, and which include a lot of popular lectures. Every month we have a lot of lectures on the popular topic in which students are interested, and today's session is one of those. We try to bring different topics in which people from across country can come and share their research. which can definitely certainly help with students who have interest in astrophysics and science, respective to astronomy specifically. So thank you so much, Dr. Ravikiran, for sharing insight and also telling what planetarium is doing and contributing in making space science and astronomy popularizing. With this, let's begin today's session. Know your star, the sun. And without much delay, I would like to give the stage to Dr. Rukmini to share her presentation. And students can post their questions in the online chat. So after the presentation, we'll be taking some of those. So over to you, ma'am.
Thank you. Thank you. Good afternoon, everyone. First of all, I would like to thank the Nehru Planetarium, Prime Minister's Museum and Library and Dr. Ravikiran, sir, for giving me this opportunity to giving this platform to share some information about our favorite star, the sun. So I would like to share the PPT. Right. So, whenever we look at the sky, mankind has been looking at the sky since ages, since prehistoric time. And we find that there are mappings of the star constellations, stellar constellations, even the caves. And not only that, man has been watching the celestial bodies like sun, moon, planets against the stars of zodiac constellations in order to realize that things are changing. They are variable in the sky, and mankind has been organizing various events and year and their own lives, their living structure that was all completely based on the measured positions of these celestial bodies. Now, since it was so much so dependent on the measured positions, mankind has started developing instruments in order to measure their angular positions. And not just the instruments, he even designed precision instruments to get accurate values of these positions, the times, as well as tried to build up different models which could help mankind understand what is the structure of this universe. Now, as we come to the modern era, we find that in addition to precision observation, angular position observation, we also have observations being taken from Earth as well as space, and that too in a wide range of wavelength bands. And one such observatory, which has worked since July 2014 until January 2025, is known as Gaia. And this Gaia is one of a very typical satellite space observatory. This observatory has been observing more than 1 billion stars accurately. Their positions have been observed accurately. We have been taking these observations for our research activities in the department as well. Now, with these observations, Gaia has produced most precise 3D map of our galaxy. Now, let me show you our galaxy. Where are we? And in this stretch of spiral galaxy, the galaxy which we call as a spiral galaxy, we are at the edge of this galaxy called as a local cloud. And within this local cloud consists of many nebulae, star-forming regions, remnants of supernovae explosions, and many other clusters as well. And within this nebulae, we are inside a small bubble of plasma, and we call this bubble of plasma our heliosphere. And we find that the solar system, along with sun and all the other bodies, celestial bodies within the solar system, is moving along with this heliosphere around the center of the galaxy at a speed of about 220 kilometers per second. And people have, how do we know about this? We know about this using Voyager observation, the two satellites which have reached the edge of this solar system. Now, before I start talking about sun, normally I do outreach. So I show young kids, school and college people, the sunspots using ordinary telescopes equipped with the solar filter. So before I start my presentation and before I start explaining them how to use the telescope to observe the sunspots, I give this warning. Do not look at the sun with naked eye at any time. You can watch it during the sunrise and sunset, but not beyond that. It is very harmful for your optic nerve. So you can either keep a filter to your in front, a goggle with solar filters to your eye, or else you can take a filter which can be equipped onto the telescope, or else the best thing would be to take the projected image from the telescope and observe it. Now, why do we want to observe sun? There was an incident in February 2022. SpaceX, we are familiar about this business, SpaceX, which is running around, sending so many satellites, string of satellites, more than 2,000 to 3,000 satellites in the Earth's orbit. Now, in February 2022, when SpaceX launched his satellites, it was found that out of 40 satellites which were launched, 49 satellites which were launched, about 40 satellites were dragged into the low Earth orbit and they were burned. They were completely made inoperable. Now, later it was understood that this was an impact due to a geomagnetic storm caused by a strong flare which was produced on the surface of the sun just before that. Now, apart from this kind of event, we also have seen in history that in 1989, in America, in US, the complete area of Quebec and northeast US has experienced a blackout, a complete blackout for one day because of the power outages. And this was also attributed to the geostorm during that event, during that period. Now we know that we live in the most comfortable zone, which is called as habitable zone in our solar system, where water exists in the form of liquid, and that is an important condition where life can sustain, life can have an origin and sustain. And apart from that, we are very lucky to have a planet with an atmosphere and a magnetosphere which is actually protecting us from the harmful radiations which are coming from the sun. Sun is providing us energy, providing us heat such that we don't frozen out, but at the same time, we are also being protected by our own atmosphere, our own magnetosphere from the harmful radiations which are released from the sun at the regular time intervals. Now, what happens because of these events which occur on the sun? Some of the events which occur on the surface of the sun are called as solar flares. And these flares generate so much of energy. There is so much of energy is released during this flare event, and so much of charged particle input is released from this event that if the the radiation of these charged particles is earth directed, then it may create a static in the electronics of the satellites, and they will disrupt the satellites in their orbits. It can also change the density of the Earth's atmosphere, upper atmosphere. The satellites may be dragged, they may fail, and there is also a high impact on the high altitude flying airplanes due to these radiation input. Now, apart from this, nowadays in the tech age, we are completely dependent. Right from the beginning of the day to the end of the day, we are completely dependent on the navigation systems, telecommunication systems. Any such activity which happens in the earth direction from the sun would also hamper these telecommunication and navigation systems, and it also affects the power grids. So these are supposed to be monitored. Such events which occur on the sun are supposed to be monitored seriously. Now, when we look in the sky, we see that we observe billions of stars of different colors, shapes, sizes. And when we want to study them, when we want to know what is our place within them, we want to find out about their origin. And the best laboratory where we can test our theories to find out the answers for all these questions would be our closest star, the sun. Now, when we talk about the origin of the sun and sun-like stars, all of them are formed in a cold bunch of cloud, which we call as molecular cloud. This molecular cloud. So, if we define the distance between sun and earth as one astronomical unit, these molecular clouds have to be as huge as 200,000 astronomical units. and it should be as cold as few degrees Kelvin, 10 to 100 Kelvin only. And in such case, you find that due to interaction, due to gravitational interaction between the particles, there is a collapse of this gas cloud, which may lead to formation of something called as protostar. Now, what is this protostar? You will find that as the gas collapses, it starts spinning, and you find that the spinning gas cloud becomes flattened, and the central most region, which is of highest density, it ends up forming a star, and the rest of the gas and dust cloud, which was in the form of a disk, has spread out, and that also can collapse individually. The fragments within that disk also can collapse and form into planetary systems. Now that creates a something like our solar system. So we have the centralmost region forms a protostar and a star, and the rest of the gaseous disk and cloud may end up forming into planets, moons, asteroids, comets. With that all we know about our solar system. Now, when we are talking about sun-like stars, let me show you this small exercise here. This is called a star in a box. It's a wonderful tool. And here you see that there is a graph which is plotted, which we call as Hertzsprung-Russell diagram. On the x-axis, we define temperature, and the y-axis, we define luminosity of the star. And we find that for a sun and sun-like star, as it begins with a after collapse from the gaseous cloud, as it comes to the main sequence, there is a band running through this graph, which we call as main sequence. We observe that this star, this is born once it starts creating its own energy at its core. And the energy which is generated at its core is due to the fusion reactions, the hydrogen fusion, which takes place, which converts into helium and releases energy. Now, in the process, this star undergoes a lot of changes. It becomes an average star, it becomes a red giant, then another phase called as an asymptotic red giant branch. Then at the end of its life stage, it just releases the outermost shell. As the center cannot sustain further nuclear burning, the central core ends up shrinking into something called as white dwarf. This is a compact object, and the rest of the shells which were enclosing this core, they end up forming a planetary nebula. So our sun currently is in the main sequence phase. That means it is generating energy because of nuclear fusion reactions, hydrogen fusion reactions in the core of its in its core. Now, when we look at the basic parameters of our sun, mass is about 10 power 30 kgs. It's too huge. The size of the sun can fit 110 Earths. The diameter of the sun can fit 110 Earths. And it is called as an yellow dwarf. It is a typical G25 star. Most of the stars which are there around solar system are late type stars, sun-like stars, and they all fit into some of these categories. Now, apart from these things, you can put a glance at some of the other parameters which tell you that at the equator, equatorial rotation period, it is approximately 25 days, but at the polar regions, the rotation period of the sun is about 33 days. So sun is made of plasma, and still we see that it is not a solid object, it's a gaseous medium, and it is at a very high temperature. At the center, it's a 15 million Kelvin, and on the surface, it is about 5,800 Kelvin. The surface which we are able to see as the sun with our naked eye, with visual photography and all, that is called as a photosphere, and that is at about 5,800 Kelvin. And we find that this surface of the sun is rotating around its axis, but at different speeds. So this is called as differential rotation. Now, when we look at the structure of this star, our sun, what do we see? We see that there is a core. Basically, at the center of this star, center of the sun, we define a core where hydrogen is fusing into helium, and at a rate of 600 million metric tons per second. Then you can imagine how much energy is being produced, right, every second. Now, this core is of about 25% to that of the total radius of the star, of the sun. And then the overlying layer is too hot and it transports the energy which is released in the core is transported in the overlying layer, which is called as radiative zone through a process called as radiation, hence the name. And above that, we find that right from 70% of the radii, you define another region called as convective zone, where the hot matter rises to the surface and the cooler matter sinks in. This phenomena is called as convection. Now, we have this as the internal structure. So we have a core, radiative zone, and then a convective zone. But what about the surface? The surface which is visible to us is called as photosphere because we are able to visualize it. And this photosphere is at a temperature of about 5800 Kelvin. Okay, and because it is about 5800 Kelvin, it is a yellow star, right? And above this layer, we have the layers of atmosphere for the sun, and we call these layers as chromosphere, transition region, and corona. Now they have varying values of temperatures. Now, when we talk about its core, this is what I meant by nuclear fusion reaction. You have 4 hydrogen nuclei fusing to form into 1 helium nuclei, and each reaction releasing about 26.73 million electron volts of energy. Now, how did we know about this? Sir Arthur Eddington in 1920 theoretically had proposed that this could be the only source which can maintain the luminosity of the sun since 4.5 billion years, whereas all other sources which can generate energy cannot support the sun to maintain that luminosity. Now, when we look at the interiors of the sun, other than core, you have this region called as convective zone. And in the convective zone, you define smaller cylindrical regions, which we call as granules. On the surface, they appear as small circular apertures, small areas, which we call as granules. They in fact are cylindrical convective cells. Now, in each of these cylindrical convective cells, hotter plasma rises upwards and the cooler plasma dips in downwards. This convection keeps transporting energy which is released from the core to the radiative zone to the surface of the sun. That is how the sun is illuminating and its luminosity is providing us energy in the solar system. Now, this is what I call as a convection. Now, in this, on the right, lower right, this black image, this is the actual surface of the sun, right? And the bubbling structures are nothing but convection process which is taking place. Now, when we look at other features of the sun, how do we know that all this thing is happening on the sun? Because there are some other features on the sun which we call as magnetically active regions. And some of those magnetically active regions are called as sunspots. They are sometimes also called as prominences. They are also called as flux tubes. And there are regions which we call as flares. And there are regions which we call as coronal holes. And there are regions which we call as CMEs, coronal mass ejections also. Now let us go through it step by step. Now in 1800s, extending the Newton's experiment, William Herschel conducted experiment to find out what all temperatures does the sun's radiation compose of. Then he discovered infrared rays through this experiment. Later, Ritter placed beyond, when Herschel conducted this experiment, he kept a thermometer beyond the red wavelength band in the spectrum, in the solar spectrum, and he could find the thermometer showing the readings. Then he understood that the invisible rays, which were actually producing heat in the thermometer, they were called as infrared rays. And when Ritter wanted to repeat this, he did it on the violet end, and he kept a photosensitive paper soaked in silver chloride, And subsequently, the blackening of the paper gave him a proof that there was ultraviolet radiation also released in the solar spectrum. So the solar light, the light which was received from the sun, not just contained the visible band of the light, the composite light not just had VGR, but it also had infrared and ultraviolet components. Later, Wollaston noticed that there are dark lines in the solar spectrum, and this is the image which was created by actually produced by Fraunhofer. It's a drawing. So these dark lines which are there, those are absorption lines in the cooler atmosphere, right? Cooler layers of the sun. Now these darker lines were called as Fraunhofer lines. Now these are all interesting things which were detected, which were observed by our peers. Now, whenever we look the sun in different wave bands, we are actually looking at different region of its atmosphere. And the first observation of sunspots belongs to Chinese even before 200 BC. But the recorded scientific observations were done by Galileo and Scheiner, who actually gave a proper scientific conclusion to the observations. Now, in 1610, Galileo used his telescope to observe the sunspots which were appearing on the sun. Now, people didn't know what these spots were. They assumed there were vehicles which were running around this planet. Sun was assumed to be one of the other celestial bodies like Earth. There must be some vehicles which were running around it, some ships which were going around it, or unknown objects which were moving around the sun, cloud-like structures which were moving on the surface of the sun. Whereas Scheiner also noticed that they must be embedded on the surface itself. They may not be just moving around the stationary sun, but they may be embedded they may be connected to the surface of the sun. Now, when they realized that they must be connected to the surface of the sun, they understood that the motion indicates that the sun is also rotating about its axis. Now, William Herschel had his own idea. In 1800, he understood he had also taken some of the observations of sunspots and understood that these sunspots must be openings in the cooler atmosphere. So the darker regions must be the underlying surface of the sun. That was his understanding. Now, what we know about the sunspots now is from this latest observations which we are able to take from Earth as well as from the space observations, space telescopes. Now, this is the structure of the photosphere when we observe sun from the Earth using a filter called as neutral density filter. So, as I said, we cannot observe sun directly. So we need to protect our instruments as well. So we use different filters to observe these suns and to image them. Now, whenever we look at the neutral density filter image, we find that there are small spots which appear and disappear, which appear to be moving along a certain direction. So we understand that they are moving along, they are rotating around the sun. They are rotating along with the rotation of the sun. And when the ultraviolet observations are done, when the observations are done by space telescopes in ultraviolet and continuum and ultraviolet bands, wave bands, we find that the photosphere is not the surface of the sun, not just the end of these spots. There are fine structures on this photosphere which appear like granules. These are the small circular regions which are there around this dark spot. They are called as granules. And this dark spot, in fact, is called as a sunspot. The centermost darkest region is called as umbra, whereas the outer shaded region is called as penumbra. You can look it in the second image here, lower second, the middle one. This is a sunspot. And in the centermost region of every sunspot, you find that there is a darker shaded region. And in the surroundings, you find that there is a grayer shaded region. Whereas outside the sunspot region, there are circular fragments which we call as granules. So what do we observe? We find that umbra, the penumbral region, the granules appear to be distorted. All these granules appear to be distorted. So we have already defined granules as convective cells. Convective cells where the hot plasma is rising from the inner layers to the surface. So there is something happening in this penumbral region, and something more is also happening in the umbral region wherein it is appearing more darker. The sheer size of each of these sunspots is too huge. The bigger sunspots can go beyond 10 to 20 Earth diameters. Now, apart from seeing their structures, apart from just observing their properties temporarily, how they are varying, it was also studied spectroscopically. So Hale in 1900s, early 20th century, he provided a quantitative demonstration for the existence of strong magnetic fields within these sunspots. So when he ran his um, spectroheliograph through through these sunspot regions, he could find that the spectral lines were undergoing Zeeman splitting. And in fact, not just detection, he also could compute the strength of the magnetic field which were producing Zeeman splitting of the characteristic spectral lines which were released by the which were observed in the light released by the sun. Now, we find that a plasma is a composition of positively charged, completely ionized gaseous substance. So it contains positively charged ions as well as electrons, negatively charged electrons. Now, when the sun is spinning, due to a dynamo action, we can understand that there is a magnetic field that can be expected along the axis of the sun, of the sphere of the sun. Now we find that since the sun is rotating differentially, that means at the equatorial region, the sun is rotating faster, and in the polar region, it is rotating slower. You find that the magnetic field lines get intertwined, they get winded up, they get closely spaced, and then emerge out of the surface of the sun. Now, when they emerge, this concept of emergence buoyancy of magnetic field lines was introduced by Parker. So he called this as magnetic buoyancy. And Arnab Rai Chaudhary was one of the first from our India. He was one of the first to do these 3D simulations on studying these bipolar sunspots by magnetic buoyancy. So we find that wherever you have these magnetic flux lines becoming buoyant in the interiors and they emerge out of the surface of the sun, they emerge out of one of the sunspots and then they end up in another sunspot. So since magnetic fields are not unipolar, you have two polarities. We find that there should be a pair of sunspots existing close by whenever they are formed. So in this cartoon, what do we see? We see the lower layer is the convective zone. There are convective cells, and apart from these convective cells, you find that there is a magnetic flux tube which is rising, which is becoming buoyant and emerging out of the surface of the sun. Wherever it is emerging and sinking, you find that those two regions are appearing as sunspots. Right? So this is a photosphere. Now, here are some of the sunspots which are imaged by the SDO. This is a video which was taken. This is the video, a composition of number of photographs, stitched photographs taken by SDO. And a close-up of the sunspots is shown here. You find that sunspots come in different varieties. They not only come in pairs, they also have a curved structure, a curled structure. And apart from this, you find that when the sun's surface is observed in ultraviolet, you find that there are streams like stream of gas which are appearing to be emerging. This is a picture of the same region of the sun taken at the same time. You have a neutral density filter showing sunspots on the photosphere, and on the right side you have iron filter, you have a UV filter which is actually showing you the region of chromosphere, the upper region of the photosphere. Now, this chromosphere is the hotter atmosphere, hence it cannot be seen with the neutral density filter. Now, since the magnetic field lines are becoming buoyant and they are emerging out of one of these sunspots and then ending up into another sunspot within the pair, you may find that the plasma flows are appearing in the chromospheric regions as loops on the surface of the sun. And not only this, you find that these structures of sunspots, they originate in the form of pores, whereas these pores are having umbral darker region but no penumbral region. And they evolve with time. Now, whenever we look at the differentially rotating sun, you find that you should not be maintaining the same magnetic field structure for a longer duration of time. Now, in 1826, Henrik Schwab, he wanted to discover actually intramercurial planets. He wanted to find out if there are any planets which are moving in the inner orbit, which much closer to the sun than the Mercury. So he was sure that if there is a planet existing before Mercury towards the sun, then it should be one second. It should be it should be happening in some cyclic order. Now, it should be creating a transit on the surface of the sun. So it should appear as if just like a Mercury moving across the disk of the sun. Any other planet which is closer to sun, which is within the orbit of the Mercury, should also be producing transits. So he made meticulously observations of solar disk for about 17 years, and he recorded in the process the sunspots which were appearing visible during that time. Now, he discovered accidentally, due to his meticulous recording, he discovered that there is a 11-year sunspot cycle. Now, what is this 11-year sunspot cycle? We find that it is observed that number of sunspots on the surface of the sun is not constant. It is not uniform. It is distributed in the lower latitudes of the sun, closer to equator, not much towards the pole. But this number of the sunspots, they keep on increasing and decreasing periodically. And he could plot it with time, and he found out that the number of sunspot number kept increasing and decreasing for every 11 years, and he called it as 11-year sunspot cycle. Sorry, one second. Yeah, no, it's good. Now, as per the recorded data of the sunspot cycles, it is observed that during 1600s, there were hardly any sunspots recorded in the history, in the astronomical observations. Now, whenever there is a solar cycle, 11-year solar cycle, when the number of sunspots decrease, we call it as solar minima. When the number of sunspots increase, we call it as a solar maxima. Now, during this period from 1600 to 1700, it was found that not much of solar maxima was detectable in the records. And it was studied by Maunder, it was identified by Maunder, and he called it as Maunder minima. Now, what are the features of these sunspots when we are looking at them? Right, we find that this is, you can see the second plot here. The first plot shows you the variation in the number of spots which can be observed on the disk of the sun, and which were observed on the disk of the sun from the ground-based observations taken on the earth. Now, when you look at the second plot, what do you see? We find that this gives you temporal as well as spatial distribution of the sunspots. Now, here on the y-axis, the latitudes are shown, the position of the sunspots can be defined. You find that there are pairs of sunspots which are existing in the northern hemisphere and the southern hemisphere. So sunspots, number of sunspots are appearing at the higher latitudes, both in northern hemisphere as well as in southern hemisphere. And then you find that their appearance keeps on moving towards the lower and lower latitude towards the equator. This typically creates a feature which is similar to that of a butterfly wing. So this is called as butterfly wing diagram, butterfly diagram. So you find that the moment the number of spots, the sunspots, start appearing closer to equator, the next immediate spot cycle would begin at a higher latitude again. The next butterfly cycle would begin. So within a span of 11 years, you find that each of this butterfly diagram would be satisfied. Now the same thing is observed in the lower diagram also, lower graph as well. You will find that average daily sunspot area as well keeps on increasing and decreasing periodically with a period of 11-year cycle. Now, Parker had given his own idea about the changes which are observed within this sunspot number. Now, Parker's idea was of turbulent solar dynamics, and he suggested that initially sun would be possessing a colloidal magnetic field, and due to the differential rotation, these field lines become toroidal field lines. Right? You can see here the first line, the first image, the cartoon shows you the colloidal field lines, and the third one shows you toroidal field lines. These field lines are parallel to the equatorial plane. Now, this kind of transformation is called as alpha effect. This is produced because of the differential rotation. Now, because you have convection happening, the convection currents during this toroidal field, the Coriolis force acting on these convective cells can twist these field lines and generate magnetic loops within these toroidal field lines. Now, resultant of all these magnetic loops would end up into a colloidal field again. So you have a transformation from colloidal magnetic fields to toroidal magnetic fields with an effect called as alpha effect, and then there is a transformation from toroidal fields to colloidal fields, which is called as alpha effect. Now, sorry, it is not moving here. Okay. Now, in 1800s, we wanted to know something more about the sun now. We were observing sunspots. We understood that the number of sunspots are changing, their shapes are changing, their sizes are variable. The regions where they appear and disappear on the surface of the sun, that also keeps changing. Spatially, temporally, you find that there is a variability in the appearance and disappearance of the sunspots. Now, apart from that, what else can be found out? We have understood that there is something called as solar chromosphere. When Augustus Young, he conducted an experiment during a total solar eclipse. Now, whenever we find that there is a total solar eclipse, the observations are like this. We find that whenever the time is recorded, the imaging is done, whenever the moon's first limb contact occurs, and then the second contact and the third contact and the fourth contact. So the moon initially covers the disk of the sun and then moves away from covering the disk of the sun. So when it is almost covering the disk of the sun, you find there is a faint glow on the boundary of the moon's disk. We call it as a chromosphere. And immediately, just before completely closing the disk, you find that a flash spectrum can be taken, a spectrum can be generated. Now, in 1870s, Augustus Young conducted this experiment on a total solar eclipse happening then, and the flash spectrum, here it is shown, the spectrum which is photographed in the bottom of the slide is actually taken by Atkinson, William Atkinson. And this kind of flash spectrum, which actually tells you about the nature of the surface, nature of the region which is beyond the photosphere of the sun. Now, so what did they find out from the nature from the flash spectrum? He could identify the spectral lines, and apart from identifying the spectral lines, the composition of the atmosphere, the temperature of the chromosphere was also deduced. So the temperature was beyond the temperature of the photosphere. It was about 10,000 Kelvin. And then during such eclipse observations, there are other phenomena which were also observed. Pierre Janssen and Norman Lockyer, they discovered helium right in our state here in Guntur. They were discovered in 1868. So when they had taken a spectra of the outermost, the atmosphere of the sun during the total solar eclipse, they discovered that there are huge structures on the surface. The disk boundary is not uniform. It was having cloud-like structures. So this was something different. It was not uniform. It was not just a spherical structure. It was having some curved cloud-like structures. So they were called as prominences. And when the spectrum was taken, it was identified that some unknown line was identified. The new line was identified. It was called as helium. So apart from this, we see that in the latest observations, in the modern observations which are done by space telescopes, the prominences are nothing but magnetic loops which are connecting the sunspots. Now, what do we observe? We find that there is plasma, a huge chunk of plasma, which is flowing from one end to other end of this magnetic loop. And sometimes it starts exploding. You find that this plasma gets ejected, it escapes the gravity of the sun and moves into the interplanetary space. Okay, got here, right. Now, other than the prominences, we have some more interesting features appearing in the chromosphere of the sun. So they are called as solar flares. Now, what are these solar flares? These are tremendous emission of energy, a burst of energy like an explosion, and which releases tremendous amount of heat and energy, and also accelerates the solar particles. Now, in 1859, this picture, this drawing was created by Carrington. Now, Carrington was observing the sunspots, and he accidentally found that there was a bright patch. You can see there are two lines which are shown towards these bright arcs, right? These white arcs, they are named A and B, and these arcs were found to be, these patches were found to be showing a brighter image compared to rest of the darker spots. So there was a brightening of these regions for about 5 minutes, right? More than a few seconds, more than few minutes. And then there was a transformation. They were being transformed. They were moving with respect to this active region. And later in modern studies, they are called as ribbon flares, two ribbon flares. Now, this was the first discovery of a white light flare, which was observed on the sun. And of course, the imaging the observations which were done here are the projected images only. They were not observed directly with the naked eye, with the telescope. And the light which was focused by the telescope was projected on a screen. And then even after the projection, the bright patches were discovered by Carrington. Now, this event was so strong that immediately after a few days, when he contacted the other observatories, people had recognized that there were a lot of auroral observations at the higher latitudes. And not only that, there was a surge of static charges in the power grids. The telegraph officers were having a short circuit, and that's why this event is the most popular event. So we understand that there should be some connection between an event which is occurring on the photosphere of the sun in a magnetically active region and the changes in the charged region of our sky, our own atmosphere, which is also influencing our own electrical appliances on the surface of the earth. Now, these flares are categorized. These are the flares which are observed by the space telescopes, and they are observed not just in ultraviolet. The chromosphere is detectable only in ultraviolet band, and not just they appear to be brighter than this region. And so you find that these flares are energized regions. They can be detected, they can be classified into various classes depending upon the energy which is released during their explosions. So, depending on the energies, the flares are classified into A, B, C, M, and X classes. And here are the values for those peak flux ranges. Now, a typical X class flare releases 100 megatons of hydrogen bombs energy. If 100 megatons of hydrogen bombs are exploded simultaneously, the amount of energy output is similar to that of an X class flare, a typical X class flare. And how do we keep monitor on all this? We have a series of geostationary satellites which are called as GOES satellites, which have been placed by NASA in geostationary orbits. There are series of satellites. They are called as geostationary operational environmental satellites. They are kept to monitor the flux of the solar radiation, not just the flux of solar radiation. They are kept to monitor monitor the earth actually. So when they are kept to monitor the earth, they as well record the flux which is released from the sun in the earth's environment, and they give us the data of these energy distributions and the classification of these flares. So whenever you find there is an X class flare, you will definitely find the amount of energy which is released from this explosion detected by these GOES satellites. One thing I would like to yeah, yeah. Now, whatever happens in a chromosphere is not just explosion of these flares, but also something else. So, what is actually happening during these flares is called as magnetic reconnection. Now, what is this magnetic reconnection? I have just now, in previous slides, spoken about magnetic buoyancy. Now, we find that there is a surge of plasma in the atmosphere of the sun, right? From the photosphere, you find that whenever you have magnetic flux lines emerging out of the photosphere through the sunspots, creating sunspots, you find that there is a surge of plasma in the upper atmosphere. Now, this surge of plasma would be restricted to move within this magnetic field lines, and you find that the magnetic there is a lot of stress on these magnetic field lines. There is a stress on these magnetic field lines whenever there is a increase in the density of the charge which is being accumulated. Now, the charges which are being accumulated create a magnetic pressure, and you find that the magnetic flux lines get snapped out and then reconnected, reorganized again, releasing tremendous amount of energy. So we find that there is a current sheet in two different regions of the magnetic field lines, and these magnetic field lines are moving towards the lower pressure region and then snap and get reorganized. This reorganization of magnetic field lines releases the magnetic energy in the form of radiation, heat, as well as kinetic energy to the plasma. So you find that whenever there is a flare created, in the chromosphere, there is a magnetic reconnection actually happening. The plasma is released as well as a lot of energy is released. Now, apart from observations which are done in continuum, visual continuum, as well as in UV and X-rays, there were observations which were done in radio as well. Now, there was this person, this gentleman, James Stanley Hay. He was an engineer. He was actually trying to find out the radar techniques to jam the German communication, telecommunications through these ships. Now, he observed that during his observations, there were strong radio interference, radio noise, which were generated from coming from the space and which were directed in the direction of the sun, which were following the sun, which were as the sun was traversing the sky, the direction of the radio disturbance was also tracing the same direction. So initially, he could not convince others about the origin of this noise, radio noise, to be the sun. But later, he had consulted the astronomers from Royal Observatory in Greenwich, and then the observations of sunspots uh, during the same period was an evidence which suggested that what all radio bursts were detected by the telecommunication networks, all the communication networks, or the jamming which was observed in the communication lines, it was having an origin in the magnetic activity which was taking place on the surface of the sun. So in 1946, when sun became very active, Stanley Hay again repeated this experiment along with his team and found a correlation of solar activity with the burst of radiations observed on the Earth. Now, other than sunspots, the flares, prominences, and radio bursts, there are some more other interesting features which we see on the sun. Father Angelo Secchi, he was an astronomer. He was observing the sun solar features during the eclipses, and he could see that there were small jet-like eruption of gases in the chromospheric region. He could identify that small hairy structures, fiery hairy structures were at the boundary of this eclipsed disk. And in the latest images, you can as well see that wherever these small hairy like structures are there, there is a change, there is a dynamical change which is occurring in the magnetic fields surrounding them. Now, these small jet-like eruptions of gases in the chromosphere are called as solar spicules, and they are supposed to be one of the causes for releasing energy, heat, causing the heating of the uppermost regions, the other uppermost regions. Okay. Now, chromosphere, here you see an image of a total solar eclipse. So what do you see? You find that the moon is covering the disk, completely covering the disk of the sun. And at the edges, you see a red tinted line, right? This is called as chromosphere. Right? Chromosphere means a sphere of color, which is glowing in red due to abundance of hydrogen actually, but very hot hydrogen. And it is very dynamic and has finely moving structures which are on the surface. And you find that there are some ray-like structures, loop-like structures, string-like structures, which are beyond the this chromosphere. Okay, so now we understand that this chromosphere, which is appearing only during the total solar eclipse, must be hotter than the photosphere, but it is cooler than the outermost region, other atmosphere of the sun, which we call as corona. Now, these filament-like structures, the wide string-like structures, ray-like structures, which are there above the chromosphere, this is called as corona, and it is an anomaly. How does the chromosphere exist as a hotter region beyond the photosphere but cooler than the corona? Okay. Now, uh, the when um, uh, so images like these actually talk about the images like these, and the studies which are done during this period, like spectroscopic studies and Zeeman effect studies, they are the key studies to give us the information about the connection to the magnetic fields in this corona, the structure and the extent at which this corona appears. The features and the structure which appear in this corona are closely representing the traces of the magnetic field lines which are existing in it. Okay, beyond this. So earlier, corona was thought to be an artifact, right? People thought that this must be due to the refraction in the Earth's atmosphere. But when two different observatories observed the similar structure of corona during an event, in a total solar event, then they realized that it's not a local effect which is occurring in the Earth's atmosphere, but definitely it is an effect on the surface of the sun. It is beyond, just around the surface of, vicinity of the surface of the sun, right? Now when Walter, he did an experiment, Edlin did the experiment, he found they studied this coronal regions spectroscopically, and they found the temperature, they found some of the lines which were unknown lines. They called it, they named it as coronium. But later they understood that highly ionized iron, calcium, and argon can also produce such spectral lines. And that's how the temperature of the corona was estimated to be about a few million Kelvin. So Walter Grotten, he found out red coronal lines of iron 10, and Edlin found green coronal lines of iron 14. And then they concluded that this could be only due to the highly ionized, high temperature region of the plasma. Now, Chapman and Cowling in 1958, they understood that if there is plasma which is an outflow flowing from the surface of the sun, then we must be immersed, the earth must be immersed in this static outer atmosphere of the sun. Chapman and Cowling just understood that the corona must be a static structure, and it must be extended right from the sun to complete interplanetary space in the solar system, and the earth must be immersed within this static corona, static outer atmosphere of the corona. Right. So the first discovery of extreme ultraviolet coronal experiment was done by something called as OSO7, right? So first discovery using an imaging was done by this instrument, which was sent into space by NASA, and it was called as Orbiting Solar Observatory 7. There were a series of Orbiting Solar Observatory experiments which were conducted, and this had an instrument which is called as white light coronagraph. Now, white light coronagraph keeps a disk in the direction of the sun. It has an arrangement where there is a disk in the direction of the sun, and it artificially creates a total eclipse. And then only the corona can be imaged. Now, the image was taken by this OSO. This is the stormy surface of the sun which was imaged. This is a postcard which was released during that time. And this observatory was one of the heavy satellites, about 200 kg satellites, and it contained more than just imager. There were more than 13, I think about 13 experimental instruments which were available in this satellite. Some were actually X-ray detectors, some had gamma ray detectors, some were ultraviolet sensors, and some were particle counters also. So there were many observations, much data was collected using this observatory, apart from discovering for the first time, imaging for the first time, this coronal mass ejection. Now, what is this coronal mass ejection? You find that the corona is not static. Corona is not at all static. Now, you find that the lower right image, the upper one is a simulation, the left one is only a cartoon, but the lower right one is the actual imaging taken by LASCO. Now, there is a coronagraph in these space satellites, and LASCO C2 observes about much closer to the sun, the corona much closer to the sun. Now, it was in 2017, you can see the corona is very dynamic, it is not at all static. There is a stream of plasma which is being released explosively, and it is moving in all directions in the interplanetary space. Right here. Now, Eugene Parker, he understood that in 1958 there should be a solar wind. He understood that high temperature and pressure in the corona with the ionized atmosphere together can cause the gas, the plasma, to expand and create continuous flow at speeds of few hundreds of kilometers per second, about 500 to 800 kilometers per second. And this continuous supersonic stream would, by the time it reaches the Earth, it would be of different shape, right? So it can encompass, it can pass through the whole of the solar system. Okay, it shapes the complete solar system. Now, we find that because of these observations, we find that our solar system, in our solar system, there is literally no vacuum, right? So we find that there is a continuous stream which is being ejected by the sun. This is a very good video which has been recorded by Parker Solar Probe. You can see here, this is a GIF which I had collected from NASA's Parker Solar Probe files, and it is detecting the coronal mass ejection event which occurred in 2022, September 5th, 2022. Now, what do we see here? You find that this coronal mass ejection, the matter which is being ejected from the corona, is not of uniform density, neither is of uniform density nor of similar speed, uniform speed. So it's very dynamic, right? So we find that our interplanetary space is no more consisting of vacuum. Now it has been converted from a space from vacuum region to a region with a solar driven plasmas. Now, this person is Bierman. In 1951, he predicted the nature of the solar wind, and he arguing that the corpuscular emission from the sun was needed to produce tails on the comets. Now, he was into a different field, theoretical astronomy field, but later, after the Second World War, he was in association with one of the colleagues in an observatory, Carl Worm, and Carl Worm had pointed to him actually in Potsdam. He pointed to him that the structure of this comet's tails were typical. They were showing some problem. Now this cutout is of Halley's comet. Now people thought that Halley is releasing its matter, and if there are two tails to a comet, you find that there are two tails to a comet, one a brighter one a fainter one, right? So for a comet which was observed in 1910, the cutout said that the fainter one was actually the previous tail which was released and it was losing its luminosity, and the brighter one was the fresh tail which was being created by the comet. Now, the same case was studied by Bierman. Bierman studied this case, and he found out that, in fact, there is a typical nature of these comets which is dependent on the solar wind. Now, that gave a new area of research, completely talking about the influence of the solar wind in the interplanetary space. Now, these comets orbit around the sun. This is a Halley's comet. And Bierman found that it had two cometary tails. So one of the cometary tail, he insisted that it could be due to it was called as a dust tail, and the shape of this dust tail depends on the speed and the influence of the solar wind, solar radiation. And the second tail was called as ion tail, and this interacts with the plasma flows which are flowing in the solar wind, right? And then they are accelerated. The plasma, the ion tail is also uh, ionized. It is interacting with the electric field which is there in the accelerated solar wind. So this second tail was in the anti-sun direction. So using using the observations of these comets, in fact, Biermann even estimated the wind speed, solar wind speed, to be about 470 kilometers per second. Okay. Right. It's no. Now, apart from this, we had to do some in situ. See, these observations were taken from Earth. The comet's observations were taken from Earth. So, solar wind, if you want to measure what is the content of the solar wind, the first measurement was done by this Russians called as using this mission called as Luna 1. In fact, Luna 1 was actually planned as a mission where this Luna 1 satellite would go for a crash onto the moon, but it missed the moon by a few few thousands of kilometers. And as it went around the sun, it could record the content of the solar wind. Now, later, after the Luna 1, later many other space missions and satellites also confirmed that there is a solar wind, there is a presence of solar wind. And for example, Explorer is there. Explorer even identified that there is a radiation belt around the Earth also, which is also modified, modulated by the solar wind. And apart from that, Mariner spacecraft was sent, and inside the orbit of to study the orbit which is closer inside the orbit of the Mercury, and it it could even identify the presence of the solar wind particles when it was closer enough to the Venus. In fact, when it was passing by through the Venus, it detected the solar wind particles. So, so these were the first evidences which supported the radiation of energy as well as matter which is released from the sun during various activities, various active periods of the sun, which we call as 11-year activity cycle. Now, why do we need to talk about all this? As I said, that it is going to impact the communication systems, it is going to impact the new technology which we are going to place in the geostationary orbits, or it can also hamper the human exploration of the space. Now, this is an artistic impression of Parker's solar probe, which has been sent towards the sun, and it is making orbits around the sun. It is taking planetary assists, gravitational assists, and going closer and closer to the sun. And on December 24th, it went just at a distance of 3.8 million miles. That is about 6.1 million kilometers from the sun's surface. It is one of the closest human-made object which has come closer to our sun. Now, what did it do? Now, this Parker solar probe takes measurements and it helps scientists understand better how these regions are getting influenced by the activities of the sun. So, we try to find out what is actually causing a solar wind. What do you mean by magnetic activity? This is not working again. Right. This is one of the coronal mass ejection which was detected by the whisper of Parker solar probe, wide field imager of solar probe, right, on 24th December 2024. Now, what do we see here? We find that CME is traveling at a speed of 400 kilometers per second to 500 kilometers per second. Now, of course, you don't find sun in the vicinity of in the image of this Parker solar probe. So there is, in fact, it is shielded from the heat and radiation which is coming from the sun with the carbon foam, and which protects all the instrumentation, and it is only looking at it. It is taking observations only of the space which is there, the solar wind which is being released from the sun. Now, when we are talking about space weather, you find that the solar wind which is released from the sun not only is detected in the form of aurora, right? They are called as geomagnetic storms. So, so Earth itself has its own magnetic field. So this is a cartoon which talks about the magnetic field of the Earth, and you find that the incidence of the solar plasma, which in the Earth direction, if there is a solar wind directed towards the Earth, if there is a coronal mass ejection which is directed towards the Earth, it has a tendency to distort the magnetic field structure of the Earth. And in the process, you find that the charged particles, the ionized particles which are flowing in the solar wind, can be trapped into the Earth's atmosphere through the magnetic reconnection, the similar concept of magnetic reconnection. You find that the slow moving charged particles, slow moving ionized particles, will be trapped into the Earth's magnetosphere and then reach the polar regions of the Earth's atmosphere. And when they interact with the Earth's atmospheric gaseous elements, they produce these vibrant colors of green, blue, and red hues, which we call as aurora. Now, this is also a LASCO image. Now, magnetized solar winds are not just restricted till planet Earth. They reach in fact till the boundary in the edge of the solar system. That's how the heliosphere is created. Okay, so this heliosphere is nothing but a interface, the common region between the solar wind particles and the interstellar medium which is existing outside the solar system. So about 100 astronomical units, you find that there is a heliosphere structure and it contains magnetized solar wind, and there is an influence. It interacts with the interstellar medium at the edge of this heliosphere. Now, how do we know about this? Voyager 1 and 2 have been providing us the information, the data for this. Now, there is another mission called as Punch. We find that the solar radiation on the surface of the sun is not just uniform. It is concentrated at certain regions and it is being emitted in the form of bursts like solar flares or coronal mass ejections. So, which need strong magnetic fields to support this process. So, Punch is an instrument which is studying this. So, Punch Wide Field Space Weather Observatory has been observing sun since long. This is a small video stitching the number of photographs taken here. So this clip of NASA's Punch satellite shows a strong coronal mass ejection emitted from the solar limb on the top here on June 3rd, 2025. And the first non-halo CME observed, right? Non-halo, halo in the sense, if there is a coronal mass ejection directed towards the Earth, the solar wind appears to be emitted in all direction. It appears to be emitted in the all direction. But if it is a non-halo, in one direction of this slide, you will observe the plasma flows. Now, what are the modern instruments studying the sun for? It is observed that the DKIST has been observing magnetic avalanches. The flares just don't happen. They are triggered by cascading effects of small rope-like magnetic strands. They twist and snap and they destabilize the magnetic field structure. And this chain reaction is something like an avalanche which happens on the mountain. And this magnetic avalanche triggers flares. So this was studied by DKIST, the Daniel K. Inyo Solar Telescope. Apart from this, Parker Solar Probe also has observed something called as switchbacks and U-turns. Now, it is observed that solar wind distribution is also not uniform in density. And unlike any conventional understanding where denser plasma may be moving accelerated with a lower speed and less denser plasma would be traveling at a higher speed, the converse was observed within this observations. So this switchback S-shaped kinks in the magnetic fields were detected by Parker Solar Probe, and it confirmed that solar wind isn't a smooth stream. Now, the probe has also mapped Alphen surface, spiky boundary layers where the sun's magnetic field loses its grip on the plasma, and the solar wind goes at a very supersonic speeds. Other than this, Solar Orbiter also has investigated tiny flickering flares happening at all the times, including the times when there is solar minima. And these tiny flickering flares all over the surface of the sun are primary reason for heating the corona to the highest temperature. Corona is found to be of 1,000,000 degrees in temperature. Now, these tiny flares, micro or nano flares, are found to be one of the reasons which could be heating the coronal region. These tiny flares are occurring on the surface of the sun. Now, it provided the first high inclination views. The solar orbiter has been changing its orbit to higher and higher inclinations such that it can also observe the polar regions of the sun. So it has been observing sun's poles. It has been raised to higher inclination views of the sun's pole, showing that polar magnetic fields are currently in a state of a flip. So this is a great achievement here. Other than that, there is a neutrino observatory by Chinese, operated by Chinese, and they have confirmed a tension in the standard model of the physics. So neutrinos are released during these nuclear fusion reactions in the core. So the number of neutrinos which are coming from the sun's core, they do not match perfectly with the models which are hypothesized, which are building them, right, which are used to study them. So it is not out of match of how much heavy material is inside the sun. So it means that the models which are built to understand the internal structure of the sun, it has to be rewritten again. Now, Aditya L1 is one of the missions which has been a pioneering endeavor, right, from our Indian side. ISRO and other affiliated institutes all over the India have contributed a lot in creating various instrumentations and working on the data which is being received. And the major science objectives were understanding the coronal heating and the solar wind acceleration, understanding the initiation of coronal mass ejections, the flares, and the near-Earth space weather, and to understand coupling and dynamics of the solar atmosphere, to understand the solar wind distribution and the temperature anisotropy. Now, this multi-wavelength study would help in understanding all these features, I hope. There are many other unanswered questions like how and where the sun's magnetic fields generate, how is it possible to predict which future activity would occur at which place and which time, right? What is the strength of the sunspot activity cycle which can occur, how to predict this, and what are the structures of plasma flows in the sun's interiors. We are observing through ground and space-based observatories the plasma flows which are in the atmosphere, in the outside the sun, but what is the structure of these plasma flows inside the sun? What produces the solar storms? Can we predict them in advance? Why is the sun's corona hot? How has the solar energy output varied in the past? And what has been its influence on the climate? How will it further influence in future? How does the sun's activity influence planetary atmospheres and its habitability? These are many questions which are asking for answers. Now, as I do outreach, astronomy outreach, there are many friends. One of the astrophotography friend has sent me a picture of Ladakh from India today, where there was a red glow aurora discovered, seen, right? So this was seen in the last, just 3 days back. There was a red auroral glow from the Ladakh at such lower latitudes. Now, last week, just the source for this auroral display is a coronal mass ejection, a halo coronal mass ejection. That means the solar wind which is directed towards the Earth, and it was recorded by LASCO C3 as well. You can see here the surge of the particles which are detected by the detector as well. Not just the imaging, even the particles are distributed. They are disturbed in the image here. Now I could attend in January one of the workshops to answer these questions, which are primary to many other questions in solar physics, not just in solar physics, but in space weather. There is this ISRO ESA heliophysics workshop which was conducted, and eminent scientists, researchers, academicians, all were there was this was a workshop which combined their ideas, and people like me were trained in using the data which was available from Aditya L1 Solar Orbiter and Proba 3. Now people are trying their different ways to find out, to use their intelligence and find out what is the best solution by which we can answer these unanswered questions. Now, apart from these activities, these our academics, we conduct. I would like to just share this information that we conduct outreach activities in the observatory. We have an observatory called as Japal Rangapur Observatory, Nizamia and Japal Rangapur Observatory. So we regularly conduct outreach activities there. We invite government and private school and college students. We in fact involve our own master students in participating and actively conducting these outreach programs. We not only show them the field trip, we not only show them the construction and working of these telescopes which are there at the observatory, we also tell them about, we also give them a hands-on experience with the telescopes. So here you can see we have arranged a telescope with a solar filter and we are showing them sunspots. So these are the activities which we regularly conduct so that the knowledge which is available with the students can be shared with the community as well. Thank you for giving me this opportunity. I hope I have completed my time.
Yes, as we come to the end of this wonderful and enlightening session, I would like to take a moment to express our heartfelt gratitude to Dr. Rukmani for such a clear, engaging, and insightful talk on the topic Know Your Star, the Sun. And we have some questions on the live chats going on during the presentation. Ma'am, if we can spare little time answering them.
Yeah.
So first question I would like to take, Nandini. Hello, ma'am. Thank you for such a wonderful session. Is there anything we wish we could measure about the sun but currently can't because of technological limits?
Yeah, Nandini, thank you for asking. Nice question, interesting. Eddington, as I have pointed out, Eddington, he suggested that he was a theoretical astrophysicist. He suggested that there is no instrument which can pierce inside the stars. Maybe we have many instruments which can look on the surface of the star and sun and stars, find out what are the features, measure them using photometry, spectroscopy, and polarimetric techniques. Right? You have in situ devices which can measure the particles which are being released, but there is no instrument which can pierce inside the star. Right? There you cannot send an instrument inside a sun or a star and to measure the parameters there. But the parameters which are there inside the star or inside a sun are directly are directly related to the activities which we observe on the surface of the star. So, however, there is a field now in astronomy called as heliosismology and astroseismology. Heliosismology is for sun, astroseismology is for stars. So there is a field called as heliosismology wherein it is possible to determine the parameters which are existing, the pressure, temperature, densities which are existing in the interiors of the star. So we just need to refine further, right? Use some advanced technical methods, programming techniques in order to contain our models and derive these values. However, the data which is being received from the ground and space-based satellites is immense. Every second you get terabytes of data. So now that we are getting abundant data, such workshops which I had attended, they are looking for different platforms where machine learning and AI models can also be developed to understand or to derive the parameters which were not possible earlier. I hope
Absolutely.
I answered the question.
Yes. So we're moving to the next question. We heard a lot about the 11-year solar cycle. Do we know what ultimately drives its timing and irregularities?
No, it is still a partial understanding. We have models which talk about we have spoken about the turbulent dynamo model by Parker. We understand that there is a cyclic change in the structure of magnetic field in the interiors of the sun, and which is evident in the form of sunspot observations. You can see that in the beginning the sunspots appear at higher latitudes, and then they gradually go towards the lower latitudes. And not only this, in the curvature of the sunspot pairs, you see that the penumbral regions are curved, and the curvature, the rotation of these sunspot regions are opposite in sense in northern and southern hemispheres. Okay, so there are some observational hints which actually um, are like going in hand with the theoretical understanding of this turbulent dynamo model. But still, all the observations which we are able to do are there. The light which reaches from sun to earth, it takes only 8 minutes time. And not just light, the matter in the form of mass in the form of solar wind or coronal mass ejection, it reaches within a day. It reaches Earth's magnetosphere within a day, less than 17 hours. So, if we want to protect our uh, telecommunication networks, the satellites which are there in the geostationary orbits or in the orbit around the Earth, or if we plan interplanetary travels in future, we need to have a technology which can predict these activities on the sun, which can predict the intensity of this 11-year solar cycle. And of course, again, there was a Maunder minimum in the recorded data. So we still do not know if 11-year cycle is an exact period. The peak of sunspot activity in every 11-year cycle, does it match? The minima, does it match? The Maunder minima, can it occur again? On what factors does it depend? So we are still having many unanswered questions which need to be answered, so, both through theoretical modeling as well as through observational techniques in order to understand the 11-year solar cycle.
Absolutely. Moving to the next question, Anmol Gandhi said amazing session, and then he
Thank you.
posted two questions. Is having a large number of sunspots good or bad for the sun itself, or does it simply indicate a particular phase of the solar activity or solar active cycle?
Nice question, Anwar. It is just a phase of the solar activity cycle. It is the result of changes in the magnetic field structure which is happening inside the surface of the sun. In the interior of the sun, whatever are the changes occurring in the magnetic field structure, they are evident in the form of number of sunspots on the surface. So it is nothing to do with good or bad for the sun, but definitely after every strong magnetic activity, like a bigger sunspot, or you have a bigger flare, stronger flare, releasing larger amount of coronal mass ejection, it may not be so bad for the sun, but it definitely is very bad for our the space weather environment.
Space weather, yes. Uh, in addition to the same question, he added another question is that do sunspot attracts each other magnetically? If two nearby spots appear, can they merge into a large sunspot or active region?
Yes, in fact, they are dynamical. They are dynamic. These sunspots do not occur individually. See, what is the origin for these sunspots? You had magnetic field lines com- converge into magnetic rope-like structures. So you had more concentrated magnetic field lines, which were emerging out after they became more and more intensely concentrated. They were becoming buoyant and emerging outside, and that created these sunspots. Wherever these sunspots were created, you didn't have any convection flowing, and they restricted the flow of convection, and then that's why the spots were appearing darker. Now these magnetic flux ropes can be, they are not fixed, they are not connected from the center of the sun to the surface. They are as a result of differential rotation of the sun. They are created because of the differential rotation of plasma which is flowing in the interiors of the sun. So you are having dynamical changes spatially, temporally. You find that number of sunspots are being created and then dissipated. Some are grouped into bigger structures, some are actually lost. Right? They are dynamical in nature.
Absolutely. So, Sing for you, I'm just taking the, I think, online name which is appearing. How close are we to experimentally confirming details of the proton chain using solar neutrinos?
That's the my last in the last few slides I had to show the Chinese neutrino observatory. It has confirmed that we are not very close, so we need to remodel the amount of heavy elements which are existing inside the core of the sun, which will actually change the rate at which the nuclear reactions can happen.
So again, we have another question from Nandini. Is there any scenario in which fusion inside the sun could suddenly change rate, or is it always extremely self-regulated?
No, definitely. See, in one of the slides, I had shown Hertzsprung-Russell diagram, which is nothing but an evolutionary plot. It tells you how the sun will evolve in future. Sun is called as a main sequence star. It is an ordinary star. It's an average kind of a star, and it is called as a main sequence star. When it is called as a main sequence star, it is understood that there is hydrogen fusion occurring in the core of the star. Now, the process of fusion is supplemented, it is supported as long as the condition for temperature and densities are maintained. Now, when then condition is not satisfied, the fusion process stops. Whenever you find that the core fusion of hydrogen is exhausted, the sun leaves the main sequence phase. And when it leaves the main sequence phase, becomes a red giant, it starts burning hydrogen in the shell or helium in its core. So when this happens, the shell is generating more energy, the core and shell are generating more energy. The envelope, the outermost regions of the sun cannot be in equilibrium, they start expanding. It is like having an unstable convection. They start expanding. Then you call it as a red giant. So you find that the fusion rate which is happening at the core, the rate also changes, and not only the rate, the region where the fusion can occur, right? The energy source, the energy can be produced by fusion. It also can be changed. It can happen in core. Next, it can happen in subsequent shells. Of
I
course, it
think
is
that
self-regulated.
you got the clarity, Nandini, on this. Moving to the next question from Ritu. If our eyes were sensitive to ultraviolet or infrared, how different would the sun appear?
It would appear very vibrant. It would appear very
Yes.
vibrant because you will see many regions. Infrared are the cooler regions, and ultraviolet are the hotter regions. And if your eyes are sensitive to ultraviolet, you are not just looking at the photosphere, you are also able to see the chromosphere and the activity. See if there is a solar flare occurring on the surface in the chromosphere of the sun, and you are watching the sun from the earth, you will not be able to see it because your eyes are not sensitive to ultraviolet. And the X-rays which are produced during these solar flares, the burst of energy they are also not visible to our eye. Whereas the CCDs and the detectors, the filters which are placed in the space telescopes, they are sensitive to these ultraviolet and X-rays, they are able to see them, they are able to detect them. So though they are happening, we are unable to see them. But if it is possible, we will be able to see the structures which are there in the chromosphere, all the prominences as well.
Anmol Gandhi replied, "Thank you so much, ma'am, for answering all my questions.
Thank you.
I
Thank you,
think,
Anand.
Anmol, that would help you
Thank you very
more
much.
in the topic. Moving to the last question for today from Astronomical Hub. Ma'am, we know that the magnet, when in molten state, lose its magnetic property. Then why do Earth have a magnetic field?"
See, the Earth there are two different things. When we are talking about the lodestone magnet and solid magnet, you talk about the domains, the regions which are actually having magnetic dipoles oriented in a particular direction. This is a solid structure. But when you are talking about the molten state, when you are talking about lava, molten lava, which is there in the underlying layers, the lower layers of the mantle, you are not talking about the solid fixed domains of these dipole magnets, right? So what is causing the magnetic field is not just existence of these magnetic dipoles in the matter, but it is the motion of these hot ionized matter which is moving around the center of the earth. So the magnetic field which is generated by Earth is not because of the magnetized solids which are existing in the interior or on the surface of the Earth. It is because of the motion of this molten lava which is moving around the. It is like a dynamo action which is happening inside the Earth.
Thank you so much for answering, ma'am, all the questions. As we come to the end of this wonderful, enlightening session, which beautifully remind us that sun is not just a bright object in the sky, but a dynamic star that shapes our climate, influences the space weather, and makes life possible on Earth. So, on the behalf of Nehru Planetarium, Prime Minister Museum and Library, I once again thank you for your time and sharing such an enlightening presentation on a very dear topic, Noah's star, the sun. And also would like to thank Dr. Ravikiran, Director Nehru Planetarium, for his inspiring opening words and his continued support in promoting astronomy and scientific temperament and the public outreach at the planetarium. So, with this note, on behalf of Prime Minister Museum and Library and Nehru Planetarium, Delhi, I thank each one of you for joining us today and making this session interactive and lively with your presence and questions. We hope this talk has sparked the curiosity to look at the sun and the sky above us with a renewed sense of wonder. Do stay connected with us for more such exciting program in future. And ma'am, in future, we definitely would like to host you for the offline session at the planetarium so that
Sure.
students can directly interact with you
Yes.
on the
Yes.
topic
Yes.
and the subject. So soon we'll be
Sure. Sure.
planning it in the
Thank you.
coming months. So with this,
Sure.
we come
Sure.
to close. Yeah, close this today's webinar. Thank you once again, everyone, for joining, and we look forward to see you again in our programs at the planetarium. Thank you, ma'am. Thank
Thank
you for
you.
your time.
Thank you very
Thanks,
much.
Rukmini, for your talk.
Thank you, sir. Thank you very much.
Yeah.